this video we're going to cover two-way between subjects factorial designs. So essentially two-way meaning there's two independent variables, and between subjects meaning that they're only between. So everybody is in a separate group, which means they're all in separate conditions. So remember that levels are for one variable, conditions are for the combinations of variables. So I'm going to use this data set with two different IVs. The first one is year, so it's either 2007 or 2008. And then transaction type, so grocery, retail, entertainment, travel, or other. Okay, so that makes it a 2x5 between subjects ANOVA. So I got 2 levels of my year and 5 levels of my type. Okay. The dependent variable is spent, so how much money was spent for each transaction. And we are going to start by looking at power, and then move on to data screening, and then how do I interpret all this output. So let's start with G power. Okay. And so G power in this one always needs to be on F test for the family, because these are ANOVAs, and ANOVA is all under F. Then under statistical test, I'm going to go down, and you've got several ANOVA options. We're only doing between subjects, so we don't want to use any of the repeated measures ones. And this one-way one is clearly not correct because we're doing a two-way design. So we're going to use fixed effects, special, main effects, and interactions. So essentially we're looking for this main effects and interactions one that just says ANOVA. Don't do ANCOVA, that's a different type of test. And so that gives me several options. First thing I want to look at is to determine the effect size. We can leave this as small, medium, and large in Cohen's F, or if you have an idea of what's going to happen, let's hit determine. Since I've done this example a couple times, I know that one of the effect sizes is really small, so I'm going to change direct over here. You'll see it says partial eta squared. Excuse me. So partial eta, because we've got multiple variables going on. Now let's make that small, so 0.01. I'm going to hit calculate and transfer to main. And you'll notice it changed the effect size F over here. Okay. I left it medium in the notes, but we can play with it here. Okay. Alpha is always 0.05. That's our P less than 0.05 criterion. Power we're going to set to 0.8, which means beta is going to be 0.2. So we only want to miss it when we should have caught it. About 20% of the time. Now numerator DF is a little harder. The simplest solution is to do number of IVs minus 1, or you can also do number of levels minus 1. So we could do 2 minus 1 for IVs minus 1, or we could actually do levels minus 1. And that's not written in the notes either, but that's also true. Well, let's do the simplest one, IVs minus 1. And the number of groups, you can do either the number of levels or the number of conditions. I'm going to tell you to go ahead and do the number of conditions because we're going to talk about power for the whole experiment. So if I have a 2x5, that means I have 10 conditions. So 2 times 5. And you generally want to do that because that will tend to overestimate the number of people. So it will give you a number that's bigger than maybe you need, which is always a good way to go. We're going to talk about sample size because more people is always helpful. So let's hit calculate. And with a small effect size, it told us we needed basically 780 people, if I round up. If a medium effect size, it was 128. It's in the notes on page 119. So you can see that power is really going to be determined by effect size, or sample size from power being 0.8 anyway. So we need about 800 people, which would be a lot. And that means that we would need about 78 people per group because we have 10 groups. So we need a lot of people. Well, let's see how many we have. So I'm going to close this. And in the data set, I think we have like 18,000 lines. So we have quite a lot of participants or transactions that we're looking at here if this were a business. So I think we'll be okay. We've got 18,260. Okay. So we're well over the 800 for a small effect size. Alright, so the first assumption that you always have to check is accuracy and missing data. And since I have such a huge data set, I couldn't just glance at it. So let's talk about how to do that. So go Analyze, Descriptives, and then Frequencies. I'm going to move everything over. I'm going to turn off Display Frequency Tables because for years spent, or amount spent, that's just going to be totally nuts. Statistics. Mean, min, max, standard deviation. We can get skew and kurtosis if we want. And then hit OK. Alright, so I don't clearly have any missing data. For year, it's coded as 1 and 2, so I'm doing good there. And type of transaction is 1 through 5, so I'm okay. Amount spent, there are no negative numbers, because that would be weird. And it gets really high, but I'm assuming that that's a correct number. So I would have to kind of know. So it seems to me like accuracy and missing are okay. Now, the notes talk about univariate outliers, so I'm going to show you how to do those, but at some point we're really going to drop univariate outliers because the multivariate outlier stuff agrees with it usually. But if I wanted to get univariate outliers because I only have one variable, so that would be appropriate, I could go Analyze, Descriptives, and then Descriptives. Just the DV. I don't care about the IV because I made those codes, so they can't really be outliers. And save standardized variables, standardized values as variables. Okay, so this is our z-scores. And then I'm hit OK. I'm going to go back to the data here and sort descending. So right click, descending, let's look at the top. So I've got a bunch of outliers at the top. But that's basically because these are the highest transactions. Okay, so that makes sense. Anything over 3 would be an outlier. And let's sort ascending. But I don't really have any too low at the bottom. Okay, so my outliers are really scores that are too high at the top. Alright, if I want to run this as multivariate though, first thing I've got to do is create myself a fake variable. Okay, so transform, compute. Let's call it random. On a function group, I'm going to click on R to get to random numbers faster. And then RV chi-square. We'll go with 7 because we like the number 7. And hit OK. So I've got my not random number plugged in here. And we'll run our fake regression to get the Mahalanobis scores. Okay, so Analyze. Regression, linear, put random in the dependent, and then just the DV in my independents. Okay, so don't screen the IVs. This is a between subjects design, so it's a little easier than repeated measures because your IVs and DVs are in separate columns, but I don't want to screen year and transaction type. I gave them those scores. Those are things that I labeled it. So I'm not screening that. I'm just screening the things that they gave me, basically, or the DV. Under plots, we're going to put z-pred in y, z-residual in x, histogram, normal probability plot for linearity and normality. Continue. Under save, we're going to put in Mahalanobis. Continue, and then OK. I'm going to go back to the data and right-click sort descending because Mahalanobis is only positive. But again, I don't know what my cutoff score is going to be. So I've got to think about this. So it's still a chi-square table. I've got 1 degree of freedom because I moved over one variable. I only used spent. And so I want to use p less than 0.001. Okay. At some point, you'll just remember that this is 10.83. But if you don't, here's a chi-square table. That's totally unreadable. Let's make it bigger. There we go. So 1 degree of freedom, 001 is 10.83. Okay, so that's going to be my cutoff score. I've got quite a bit of people up here at 10.83. Goodness. Let's see. There we go. 132. And you'll notice that that's the same set of scores for z-scores, but z-scores actually found more than Mahalanobis did. Okay, and that is because technically the cutoff for z-scores is a little bigger than 3. We just use 3, but they tend to agree. Okay, it's not perfect, but they do. And I actually am not going to delete anybody. So this is a case where I know that all these scores are accurate and they're actually reasonable. They're just really large. And so in this case, this is a time that I wouldn't want to delete outliers because I know that they're appropriate. If I'm dealing with participants, like real people, like this is sort of data that isn't people-based. You might have had gotten this from a company or something. But if I'm working with surveys where people are answering things and they're likely to get bored or not be really willing to do your survey correctly, that's when I'm definitely deleting people. Because anytime I feel like participants can be dumb, that's when I think outliers are important. But when it's like real data, I tend to not delete it. So let me give you another example. We've worked with surveys where we're working with big data, so to speak, where we get a bunch of databases from people that have been normed. So they've done a lot of work on these databases. And there are scores in the databases that seem crazy. They're either way too low or way too high given everything else. But because it's normed data, I know someone else has worked on it and looked at it, we don't delete the scores because while they're an outlier, they're still part of the data that we were looking for. So they're part of the population I'm interested in. Okay. So outliers really are your choice to delete or not delete. And in this case, I'm not going to delete them because I know that I have a good reason to believe that they're real scores. They're part of what I'm interested in. Okay. So I'm going to leave them in. Because I've left them in, I don't need to rerun any of my other analyses. So I'm going to pull up that window. And the next one I've got in here is linearity. And it looks a little different than the one I have in the notes, but I'd say it's okay. It's starting to be bad because it's got this kind of bow shape. So we might have some data that is sort of curvilinear, but I'm not too worried about it because I have 18,000 participants. But this bow is a little worrisome. All right. For normality, I can go back and look at my skew and kurtosis values. Okay, so I just skipped up to the top. And for amount spent, the skew is less than 3, so it's okay. And the kurtosis is less than 3. So univariate normality is okay. If I look at my histogram, though, that gives me a slightly different picture. Okay. Most of the data is between 2 and 2. But we do have this problem where it goes all the way out here to 8. Now those are just really tiny frequencies and you can't quite see them because of the way the graph is rendered. But it's problematic that it runs from 2 to 8. Okay, so this out here is not good for you. Because we have so many people, I would say it's probably okay, because normality is the one you can bend the most. You need at least 30 people, and then most of the time your analysis is correct, or at least appropriate, because of the central limit theorem. But this is an example of one that you would probably want to figure out why. And that's because I left the outliers in. If I took those outliers out, that would go away. It would probably be 2 to 4. Okay. So I'm going to go, yeah, okay, that's probably my outlier problem. Okay. And then the next one would be homogeneity. And this is a great example of something that is totally bad. Okay. It's slightly turned from the one I have in the book, but you could still see this is like excuse me, a great example of the megaphone effect. So you do not want to see this. So look at 0 here, and it runs from essentially a little over -2 to 6. That's not good. And then it runs 2 to 8, or 2 to 6 1/4. That's also not good. So this is a great example of one that homogeneity is bad, and if we were to check for it, homoskedasticity would also be bad. We're not really checking for homoskedasticity because this is ANOVA, but if we were, this would also be bad. Okay. So this makes me nervous. It's not good. Okay. What I can do now is look at Levine's test and see if Levine's test is significant, and it probably will be. Alright, so we've run through data screening, and they're not so great, but this is made-up data, so, what can you do? If you were to really have these problems and it were your thesis or a big project, I'd probably tell you to try a non-parametric test as well and see which one gives you a better answer. They tend to actually agree with really large samples, and what'll happen is you'll just lose power when your assumptions aren't met. And so you might miss an effect you're looking for whereas in a non-parametric test, you might still see it. The problem with a non-parametric test is that sometimes it's hard to interpret, or people have trouble with them because they're not as common as ANOVAs. Okay, so there are pros and cons on both directions. With about 18,000 people, I don't think you're going to lose too much power because you got a lot of people. Okay. So let's try running the real ANOVA. Okay. So analyze, general linear model, okay. And it's still univariate. Remember, this should be labeled between subjects for 1 dV. I'm going to stick my amount spent in the dependent variable and my 2 IVs into fixed factors. Okay, so nothing into random factors, and covariate is ANCOVA. Under post hoc here, I'm going to move over both of them. Okay, it's going to give me an error message for year because I only have 2 levels, but that's okay. We'll deal with that in a minute. And then remember, you have lots of options, but Tukey is kind of the most appropriate one in the sense that it's not super conservative and it's not super restrictive either. So, I said the same thing twice. It's not super conservative, nor is it super liberal. So it's kind of right in the middle. It's your like middle of the road friend. So continue. And then we're going to click on options. Okay, I'm going to highlight all of these bad boys and move them over to display means. Okay, remember, we clicked on this for repeated measures, but we have the Tukey option, so I'm going to leave that one alone. Descriptives, effect size for partial eta squared, homogeneity for Levines. The descriptives is a little repetitive because it does give us the means already, but this is the one that gives you marginal means, so you need this bad boy. Okay, so hit continue. And this is not in the notes, but I think it's something good that you can add so you can just sort of visualize what's going on. You can click on plots, stick one of them in horizontal and one of them in separate lines, and hit add. And then if you aren't sure which one you want, do the reverse and hit add. Okay. What that's going to do is it's going to give me a line graph of the means. Okay, no error bars, no fanciness. But sometimes it's helpful when you're just looking at it and you're like, okay, well, I got the interaction. What the heck does that mean? So I think sometimes visually I can see it better if it's a line graph. Now, line graphs aren't really appropriate to put in journals because this is not continuous data. I guess year is sort of continuous. So you'd rather have a bar graph. But in just terms of like your sanity, sometimes this is easier to see. Okay, so hit continue and then okay. And we'll walk through each piece of the output here. Alright, so first thing it did was it gave me a warning. It said post-hoc tests are not performed for a year because there are fewer than 3 groups. Okay. Essentially that means that when there are only 2 levels, it does not want to run the post-hoc for you because it's basically like, hey stupid, you're not supposed to do that. So when you run an ANOVA, on only 2 levels, it is a t-test. So you don't have to repeat and do it again. So that's what happens to people a lot of times is they run it and they have 2 levels and then they also run a t-test, but you've done the same test twice. Don't do that. If you run the ANOVA and it only has 2 levels, there's actually no post-hoc for the main effect. And so that's why SPSS actually will not let you do something you're not supposed to do for once in its life. And it tells you don't do that. Okay, so that's why you don't get that output. It's not broken. It's because you're not supposed to run that sort of test. Next things it gives me is each level separately. So it tells me how many people are in each of the separate levels by IV. And if you ever have a trouble with a test, this is where I tell you to go back and look. And this next box, this descriptives box here. So one problem that you'll have that you'll lose power for is really unequal sample sizes. And especially if it's like 8 to 1 or 80% to 20% is the way I think about it. You would love it to be 50-50, where everybody is equally separated between groups. And ours is pretty close. I mean, it's not perfect, but it's pretty close. We've got more in this retail group than anything else. But if you start to have like 80 participants in one and 20 in another, so that's a 4-to-1 ratio, I guess, you're going to have trouble. 5-to-1, definitely going to have problems. And that will just, what it does is you lose power, because it's hard to compare to that smaller group, because the variances are going to be large because you have less people. So remember, less people equals bigger variance. Bigger variance is not always good for you. And then sometimes the ANOVA will just like crash and not run. And then this is where you want to look here. So what this descriptives box tells you is the mean for each condition. So for 2007 grocery, here's my average, my standard deviation, and my N. So this is a really good box sometimes for post hoc Cohen's-d calculations. Okay, so 2007 retail, mean, standard deviation, N. And if you end up with one of these boxes with less than 5 people, it's really going to be cranky with you. Okay, so this is where you can kind of check and make sure you have enough people in each condition. You can also do that in cross tabs, but this is right here as part of your output, so it's a little easier to just kind of look at it. We clearly have enough people in each group. I don't really love this box because it gives you the 2007 totals and then the totals down here, and it gets really confusing. But I do like the fact that it tells me in, so I can kind of quick glance, make sure I've got enough people in each group. Alright, so back to what the actual notes have. So 125 here gives me Levine's test, so this bad boy. Remember, we do not want 0, 0, 0, so this is the new kids on the block rule, no O, O, O. And so that is significant. It is bad for us. With homogeneity, there's just not a whole lot you can do that doesn't involve switching to a different type of test. Because if you're dead set on ANOVA, you just kind of have to admit that this is not the best thing in the world and move on. Okay, so you would just tell people homogeneity was significant, but we have really large n's, so that's probably their issue. Okay, remember, we talked about how Levine's test is highly sensitive to n, because it is basically an ANOVA on variances. And so sometimes if you have really large samples, it will be significant no matter what, and I think that's what's going on here. Now, granted, this is also really bad, so this is a good indication that it's like not just the n problem. But remember that Levine's is biased by sample size. So if you have a large sample size, which is usually normally over 100, but here we've got a lot more than that, sometimes it's significant just because that's the way power works. Okay, so it's not always the most helpful test to run. Alright, so I'm going to take this between subjects effects box here, because that's where all the dirty work is. Stick it in Word so we can kind of type while we do this. Maybe. Oh, okay. Random thing. Let's try again. There we go. That looks like an ANOVA and not a birthday card. Okay, so the first thing you want to note is that you've got a lot more F's than you've had before. So I'm going to remind you that these first 2 lines are things that you don't need. So I'm going to mark them out. And these last 2 lines I don't need. I'm going to mark them out. Okay. So what happens when you run a factorial ANOVA is that you get multiple F values because it sort of runs 3 little mini ANOVAs for you. Okay, so the first thing it does is it gives you a main effect of your first variable. Okay, which in our case is year. And what that means is that, make this bigger for you, it's run an ANOVA as if year was the only thing. Okay, so these are the main effects as if the other variables didn't exist, which tells me if that IV all by itself was useful. Then the second thing it's going to give me is my main effect of my second variable, which in our case is transaction type. And that is an ANOVA ignoring the effects of year. Okay, so this is like if you only had one of the variables at a time and you ran a single ANOVA and then a separate single ANOVA. The reason you don't do that in real life, though, is because you actually are usually more concerned about the interaction. Okay, so this would be year by type. Because if I didn't care about the interaction, why am I running them together in the same ANOVA, is the point. Okay. So I really want to understand the interaction. I want to test for it. It's my thing. Otherwise, I wouldn't have put these 2 variables together. And I wouldn't certainly be running them in one ANOVA because that makes your life more complicated. I would just do one or the other. So we're mostly concerned with the interaction, or why are you doing this type of ANOVA is my question. But it does give me each main effect. So let's talk about each one separately. So the main effect to my first variable here is year. And I want to write that out. So I'm going to get my F here. And then what I'm going to do is use this column for my degrees of freedom for both of them. So let me highlight that here. Now, I got one column for error. And that is the second degree of freedom for each one. So I've got year and then error, type and then error, year and type and error. So when you only run one way ANOVA, there's only 2 lines. That makes it really easy to use. But when you have multi-way ANOVAs, you get lots of lines. So which one do I use? Well, I want to use this first degree of freedom, and then my second one is always under error here. Okay, so I'm going to do 1, 18, 250. Okay. And it's 1 because it's year is 2 levels, minus 1. 18, 250 is n minus 1 plus n minus 1 plus n minus 1. Okay, and we had 10 groups, so we had 18,260 people minus 10 groups. Okay. Next thing I want to use here is my F column. So I've got, it's equal to 4929. Okay. And then I want to use sig for P. Excuse me. So P is less than 001. Remember, don't do equals 0, 0, 0 because probabilities cannot be 0. And then I've actually got partial eta squared. So this time it really is partial eta squared. Every other time when you run a one-way design, it still says partial even though it's not. Okay, so what is partial eta squared versus regular eta squared? So partial eta is the effect of that variable all by itself, okay, ignoring the other variables. Whereas regular eta is the effect of that variable including all the other variables. So you will get r squared down here. But we're not going to use that because that would be like overall. How much do all of the variables account for variance total? Okay. Instead, I want to think about each variable individually or each effect individually because the last piece is the interaction. And so I'm going to talk about the partial effects. And so essentially partial effects are like if I looked at only that variable, here's what that variable is doing for me. Okay. Whereas r squared is how much are all the variables doing for me. Okay, so I'm going to break it down by variable. Okay, so that's going to be eta, which is the little curly n, and then a little p, and then squared. Okay, so if I wanted to get super fancy, the p would be subscript, and the 2 would be superscript. In the notes, the p's are missing, so it should have the little p on there. I'm going to do 0.003. Now remember, you could also list this as less than 01, because that's correct. So you could do eta squared is less than 01 or eta squared is 003. So this is significant. And then we'll work with like what does that mean for me next here in a second. So I'm going to do all my F's at once. So for type, I now have 4 because I had 5 levels minus 1. It's still 18,250 as my second number. My type variables 580.4. And then P is less than 0.001. And eta squared partial is 0.11. Okay, so this is a medium effect size. Whereas this one on the top is a small effect size. So remember the rules are 0.01, 0.09, 0.25. And this one's also significant. Okay. And last but not least, we're going to do our interactions. So F, and it's 4 and 18,250. Okay, so got that from here. 4 and 18,250 is 3.47. Our p-value is 0.008. Okay. You could also list this as p less than 01 because that's true, and p equals 0.01 if you round it up. So either of those options would be appropriate. Don't do all three, just pick one, but I'm trying to show you there are a couple of correct answers here. And then I would say eta squared partial is 0.001. So this is a really small effect size. Okay, sorry, wrong button. Okay. Also significant. And then here's where we have to make a decision, right? So if I am analyzing this data and I have three significant effects, so I have both of my main effects are significant and the interaction is significant, and I were doing this for a project, I would just look at the interaction. Here's the deal. If you're doing a two-way or multi-way design and you're interested in the interaction and the interaction happens, just look at that. Because the main effects are essentially ignoring the effects of the other variable. If you have said the interaction is important, and we'll get into more in a second, I'm like, what does that even mean that it's an interaction? Okay, we'll look at the graphs. Then why would I ignore the other variables? Okay, so if I have said both of these variables are important, I need them, they interact with each other in a way that is interesting, then why would I then go back and say, well, let's just talk about one of them at a time? So I am of the camp that if you get this interaction, just analyze the interaction and ignore the two main effects. Now that's not true for everybody. Some people say you should analyze every significant effect, and that's cool too. But for me, it's like, if the interaction is important, let's just analyze that. So let's take a quick second and talk about what interactions mean. To do, excuse me, to do that, I'm going to go back to my output and look at the plots that we got at the very bottom. So I've got two different options, and I'm going to copy these. Sometimes they're really cranky. It's JPEGs. Oh, gracious, that's huge. Shwink. Here we go. And my other option. So these are two different ways to look at the interaction. Let's stick them next to each other here. All right. And so what's happening? If I look on the bottom here, it's talking about the type of transaction. Okay, so I've got that separated by year, or year and then the type of transaction are the 5 different lines. So I can look at it either way. I personally am preferring the one on the left for this specific example because it makes more sense. Okay. And so what I could do is look at the pattern of the different levels. And so interactions mean that the patterns of the levels for each variable are different in some way. Okay. And so that means that these lines are not perfectly parallel. Okay, so parallel lines means there's no interaction. And so the grocery ones are kind of close together. The retail ones are further apart. Entertainment's pretty close. Travel's further apart. And so you're getting this interaction because these pieces up here are not the same distance apart. Okay? You're getting the main effect because they are different from each other. Like grocery is clearly lower than retail. But I'm getting the interaction because across those years we're getting differences between the pieces. So grocery's kind of close and then retail's further apart. Okay, so that's the interaction. So when I think about interactions, to me it means that both variables are important because the patterns are somehow different across those variables. If I looked at it for year, the way I would see it, and this one's a little more subtle, so that's why I don't like this graph as much, is that the difference between the years is different. I mean, clearly the lines are not the same, so that means that the retail has the highest spending. But if you look at the drop in retail, it is stronger than the drop down here for these types of year, for grocery, okay, which is the same thing I was saying over here. So this one's a little more obvious, but you never know which one's going to be better to see, so that's why I did both. So interactions to me are always, it matters which group I was in. I need to understand both variables at the same time together, rather than just one variable at a time. All right. So all that being said, I would normally just analyze the interaction, but since I'm trying to teach you how all this works, I'm going to talk about how might you analyze the main effects at the same time. So to do that, I'm going to pull up my marginal means here for year. See if we can get it to copy. Not too much trouble. Oop. Nope. SPSS is really silly sometimes. Here. Let's do a screenshot. Okay, there we go. All right. And so what are marginal means? So you'll look at the SPSS output and you'll see that it says estimated marginal means. What is that left over from? Essentially, what that implies is that these are the means in the margin. So let me make you a chart real quick, because I'll need this here in a minute. Whoops, tables. So we've got 2 types of years and 5 types. So let's say this is 07, 08, and this would be grocery, entertainment, retail, travel, and other. And so if I had all the scores in here, so this is my levels on the side and my conditions in the middle, essentially the marginal means that I have here are the scores ignoring the other variable or the ones out in the margin. Okay, so if I were to average all the way across for 07, all the way across for 08, those scores would be 286, 267. Okay, so they're the scores ignoring the other variable. So this is back to if you ran the ANOVA and it only included one variable, right? So it matches my ANOVA numbers here. Now with this, there's no post-hoc test. There's only 2 levels. You just look at the means. So I would say that 2007, I spent more money than 2008 on each individual transaction because the mean is just bigger. And I actually don't even need a effect size because I already have it. So I need to square it up here. So I already know it's small. So there's nothing else I have to do when I only have 2 levels. I just look at the means and I say, look, this one's bigger. Okay. You could make a chart, but we're going to make an interaction graph, so I don't need an individual one for this. All right. On this second main effect, though, I have 5 levels, so it's not that easy. So I'm going to copy type of transaction here. Come on now. Turn off the annoying camera noise. There we go. And so I've got my differences in means here. And so if I wanted to analyze this, I would be looking at doing essentially a one-way ANOVA post-hoc. So that would be an independent t as my test, and we pick Tukey as the correction. This would be the test type. This would be the correction. Okay. And fortunately, SPSS does that for me. So I would scroll down further and get this gigantic post-hoc box that we've already looked at before. Would copy that bad boy and stick it in here. So this is going to be a big table. But what I could do was then take that post-hoc box and create the kind of tables we did before. So we had mean 1, mean 2, p-value, explain that to me what that means, and the d. So this is that same table I've been making. And so I could say, okay, I want to do grocery, which is 191.46. The standard error here, 3.010. So mean an SE, so I can remember here in a minute. And then I could compare that to retail, which has a mean of 371.06 and an SE of 2.78. So I would scroll down and look at my Tukey tests. So I got grocery versus retail. The p-value is 0.000, so I would say it's less than 0.01. And the explain box, I really want you to tell me what the direction is. So retail is higher than grocery. Okay, I spent more. in the retail category than I did grocery. If I wanted to calculate D, I could use MOTE. And this is going to be under, so click on Measures and Independent T. And then I would fill in these numbers I just got. So 191.46, 371.06. I'm going to ignore my 2 standard deviations because I have standard error in this box, so that's the tricky part. Just make sure you're using the right standard whatever. And then I also need N. So here's my problem. I don't have N easily at the moment, right? Because I have this box, and I have this box, but no N. Okay, so where can I get N from? And that is why, God bless, these 2 boxes. Okay. So I'm going to copy both of them. Let's stick that, where are we at? Here, for my interaction. Okay. And so for grocery, I have 3543. Okay. And I could look at this box, but I think it's confusing because you'd have to go down here. So I'm going to save the second one here for my interaction test here in a second. But for right now, I've got grocery as 3543. Put that up here. And for retail, 4419, so right here. Okay. And so that's another reason, like I said, why I love to make these boxes, because it really helps me think about all the numbers I need to be able to do the things I would write up. So at 3543, plus I make really great tables later. 4419. Now I didn't run T, so I can't test if that T is right, but this is a big difference. So I'm going to come down here and look at Cohen's D is negative 0.79. Remember, the negatives don't matter, so I'm just going to say, oops, 0.97. Sorry. So that's a large effect size difference between the two. I mean, look at the means. It's 191, 371, so it's a pretty big difference. And then I would keep going, so let's just do one more. And do grocery versus, who's next? Entertainment. So my mean for entertainment's 22918. My standard error for entertainment 3.31. And in, go down here to this big box, 3102. So you do get all the information you need from SPSS, just in very different locations. Okay. So I'm going to look at SIG down here. So grocery to entertainment is 0.000, so less than 001. Okay. And I would say my entertainment is higher than grocery, because the mean for entertainment is just bigger. And let's calculate D real quick. So I got 191, that's correct. So 22918. My standard error is right for that one. I got 3.31. And my N values, 3543, 3102. So Cohen's D for this one is 0.2. So it's a much smaller difference than the first one, okay, which makes sense. Those means are closer together. And for this main effect, I would just keep trucking. Okay? Because there are 5 levels, there are going to be 10 tests. So I've got grocery versus retail, entertainment, travel, and other. So that's 4. And then I would have so grocery, retail, travel, entertainment, other. So that's 4 of them right here. Retail versus entertainment, travel, and other, plus 3, so that's 7. Entertainment versus travel and other, plus 2, that's 9. Travel versus other, that's 10. So we have 5 levels. There are 10 pairwise comparisons. Okay. So that is 10 post hocs that I would have to talk about. Okay. I'm not going to do that. I wanted to show you how it works in case your interaction doesn't come out significant. You know what to do. But because my excuse me, because because my interaction is significant, I don't want to do that. So I'm just going to ignore it and look at the interaction. Okay. If your interaction wasn't significant, this is what you would do. All right. So last but not least, let's talk about this interaction. So we've been saying this is what we should do this whole time, so now I'm going to do it. Okay. And I am now on page 129-ish. So the very first thing I'm going to do is fill in these means. Now you could do this box. I'm going to fill in this box, but I'm going to add my means, my standard errors, and my n, so that when I get to doing this in my post hoc box, I've got all my numbers I need. So this is kind of an extra step, but for me it helps me understand which way I'm going to analyze the interaction, and then it also means that I have all the numbers I need to do the post hoc test /D. So I'm going to take these means and standard errors from my marginal means, which is kind of a misnomer because this is no longer marginal means. Excuse me. So it gives me this box out here. Those are conditional means, okay, because they're for the conditions and not the levels. So it's kind of funny because they're always called marginal means, but they actually shouldn't be. Okay. So I'm going to fill this in. So I got 197.58. Standard errors 4.27. I don't have n yet. I'll come back to that. 185.33. Standard error 4.50. So you could probably fast forward and see how fast I can get to talking here. Oops, skip one. 3.845. Just keep going across, actually. Did I do them in the right order? Oh, gracious, no. So let me relabel this here. That would have been bad. All right, so entertainment 235. And then when you get really savvy at doing this stuff, you can actually cut and paste these tables into Excel. I just am doing it this way, so it's really clear what I'm doing, and it's not looking like a bunch of computer magic. I'm going to fill in this last one here, so 352.50. Alright, and then 222.73. And last but not least, okay, so that should be close enough. Right, so I've got all of my means entered. Now I've got to figure out n. So I'm going to come up here, and that's where this box, excuse me, that's where this box comes into play. And this is the only place that you will see conditional in sizes. It's in this descriptive statistics, the first version of it. And so I can get I find this box confusing when it comes to making a little chart I just made, but you could use mean and standard deviation, so it doesn't matter for mode as long as you have one of them. But you do need it because of n. So I've got 1866, right, 2296, 1619. So just make sure you're doing it in the right box. So I got 07. I'm doing 07 up here. Okay, 7, 5, 20. Whoop, whoop, whoop. Now I've forgotten. I'm so excited about it scrolling. 17, 15, and 2090 here. Okay. And then I've got 1677, 21, 23. And then 1483, 1504. And then 1887, I think. Yeah. Alright. So now I have all my means in one place that I can use to do my interaction. Okay. So how do I analyze this interaction? Well, we've talked a lot about like, well, okay, it's this differences in levels across both variables. So I'm going to go back down to these pictures and talk about it this way. Okay. So what I can do is I've got to split something. So when you have multiple variables and you get an interaction, you can't just like magically make it happen in SPSS. You have to split the variables up somehow. Okay. So I could split the variables here by type of transaction and analyze these two dots together and then analyze these two dots together. So let me see if I can do something fancy here. So I could analyze these two dots together. Oop, I didn't like that, but you get the idea. Or these two dots together. Right? Or these two dots or these two dots. We're just being too fancy. And so that would be breaking it down by the type of transaction. It's essentially, and I've got this kind of explained at the bottom of 129, is I would be analyzing grocery 07 versus 08, retail 07 versus 08. Or what I could do is analyze by year. So I could analyze grocery versus retail versus entertainment versus travel versus other, but for 2007, and then do the same thing for 2008. Okay, so let me kind of write out how that would look. Okay, so I got two options. So let me fake make some post-hoc boxes here. Got group 1, group 2, P, explain, and D. Okay. So I could do, oop, don't be smarter than me. There we go. Grocery 07 versus grocery 08. And you'll notice that it's got two labels. When I was analyzing the main effector earlier, it was up here, grocery versus retail. Okay, so why now is it grocery 07? Scroll, 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 scroll. Because I'm analyzing the interaction, I have to think about it as conditions. So remember, conditions are the combinations of levels. So it's grocery 07, grocery 08. And then I could do retail 07 versus retail 08. And so essentially what I'm doing here is analyzing going down. So I'm comparing these two to each other, and then these two to each other, and then these two, etc. And that would mean that there would be 5 tests. So let me fill that in real quick. Because this is the one I'm going to do, and you'll see why here in a second. Travel 07, travel 08, and then other 07, other 08. Okay. So there are only 5, because I'm only going to compare these two, these two, these two, etc. Okay. And that would be going down. Okay. And by down, I just mean I'm like analyzing it by column rather than row. You can analyze going across or down, only pick one though. So across or down is just my way of thinking about it, like it's not like a traditional term, but that just means like analyze it going down the columns and compare column cells to each other, or analyze going across and compare row cells to each other, but don't do both, just one. Okay. And so that, if I analyze it going down on this way, that's going to give me 5 tests. The other option would be to analyze going across. So I would say for 07, I'm going to compare grocery to 07 for retail. And then what I would do is 07 grocery, and then 07, what's next? Entertainment? Yeah. And I would keep trucking. 07 grocery versus 07 travel. And then I would have to fill that in 10 different times, because that would be 10 tests. Grocery for retail, entertainment, travel, and other for retail to entertainment, travel, and other, plus 3 is 7. Entertainment to travel, and other, plus 2 is 9. Travel, and other is 10. Okay, so each row is going to be 10 analyses. So together, that's 20 different posthocs. Oh my god, that's so many, right? And so essentially what would happen is this table would keep going, and then we do the exact same thing for 08. Right? So we would do 08 grocery versus 08 retail. And then we would keep going. And I'm not going to fill in 20 different tests. You guys are already probably bored with all my tables. And so which way do you pick? And there are two sort of options. Okay? The way I always think about it is theory comes first. So if you have a specific research question, go with that. Okay? That's always the most important thing, because you design this research study and you have usually a specific question on the interaction, or sometimes it's just there's an interaction, let's see what happens. But if you have a very specific direction, do that. And I've had a couple studies where it meant doing the long way, but we had a very specific question. Okay? If you don't have a specific question, go with the shorter way. Go with the lazy route. It's not lazy, it's less post hocs, which means less type 1 error. So it's the statistically appropriate lazy way. Okay? And what that means is go with the one with the less rows or less columns. And since I only have 2 rows, that means I'm going to analyze going down. If this down thing versus across thing confuses you, just think about it as analyzing it by the smallest number of options. Okay? And if you aren't sure which one is the smallest number of options, you can write them out, like what I just did. Okay? And clearly, this way, comparing these two and these two and these two, is the smaller number, because it's 5 tests versus 20. And I like 5, that's much faster. Okay. All right, now, I've decided to do this table. So we're going to fill in this P, D, and explain. However, where are my numbers? Okay. I've reached the end of the SPSS output, believe it or not. There's so much output right now. But where are those? Okay. And God bless SPSS, they have all the money in the world now that they've been bought by IBM, but they can't seem to figure out post hoc interaction effects, so we've got to do it ourselves. Okay, so now I've reached the end of page 129 and the start of page 130. Okay. And this is split file. We haven't used split file in a while, so we're going to go back to it. Okay. So let's go data, split file, not split into files, split file single, and I get this window. Okay. So what am I doing? I'm essentially splitting the variable up so I can analyze it. So let me go back to Word real quick here. I want to compare grocery 07 to grocery 08. In my t-test window, I can't say compare column 1, row 1 to column 1, row 2. Okay, it's not that cool. That would be awesome, because then we wouldn't have to do any of this. But I can't say compare this cell to this cell. Okay, SPSS for independent t, it's like you get one variable at a time. So I'm going to coerce it into thinking that these are different files so I can get down to my one variable at a time. Okay. Because I want to know each one of these separately, grocery, retail, entertainment, travel, I'm going to split on that variable. So whichever way you decide to go, I'm going down, I'm going to split that variable up. So because I'm going down, I'm splitting this column variable up. So because columns, I'm splitting by columns. That's a little easier to think about. So click Organize Output by Groups and move over Type of Transaction, because that's my column variable. Okay, hit OK. If you do this the wrong way, you'll get an error when you try to run your independent t-test, and you'll know, and so just split on the other variable. So if you mess it up, it's easy to fix. Now we're going to run independent t. So that Posthoc test is still an independent t-test. Is independent t. And I actually don't have a correction. At the moment, we're not going to run a correction because there's only 5 tests. And I'm actually kind of covered by running the ANOVA. Okay. If you wanted to run a correction, I hate to say this, but Bonferroni is your easiest option. So in the repeated measures notes, I talked about how would I calculate Bonferroni by hand. But essentially what I could do is take my alpha, which is 0.05, that's our p less than 0.05, divided by the number of comparisons, right, which would be 5 in this instance. And so I would now look for a sig value of 0.01. So you could correct. For some reason, it is not super common to correct interaction tests. And here's one reason why. If I run the ANOVA, I'm actually covered for a certain number of post-hoc tests. Okay? It's the same as the number of degrees of freedom in the first DF slot. Okay? So that's way up here. I'm actually covered for 4. Okay? There's a really long story why, but you are. And then up here, I actually would only be covered for 4 as well. And so that's why we ran Tukey, is because we ran 10. Or we would have done 10. Okay. And so people don't always correct because they think they're covered. And I'm not going to correct because I'm not running any other tests. So I didn't run the main effect test. I showed you how they would work, but in real life I wouldn't run it. So because I'm not running the test for the main effects, I'm going to let my interaction kind of be part of all of that. Okay, so I don't tend to correct here because I'm not running a bazillion tests. Now, if I ran it where I had 20 tests instead of the smaller version for 5, I definitely would do a correction because 20 is a lot. But, you know, for, I think I did this again. Anyway, just for fun, let's say it's 2 N's, 3 N's, and 4 R's because I can't ever seem to get it right. And so I am not going to run any type of correction, but if I did, it would actually be really easy to do Bonferroni. So 0.05 divided by my 5 comparisons. But again, I don't have these p-values, so let's run the test. Okay, I've split my file, and what that's going to do is it's going to give me this t-test for each level of the type variable separately, which is what I want. Okay. So let's go analyze. Compare means, you just thought you were done with this box. Independent t. I'm going to use year, so whichever variable you split by, don't use it here. And be sure you're using 1 for split, 1 for test. Hit define groups, and I think it's 1 and 2. Let's go with that. Continue, and then my amount spent is my DV. I'm going to stick that in test variables, and hit OK. So look at what it does. It gives me each one separately. Yay! Now, I had already made this huge box here, and I had done all this work already. However, now that I've run this and showed you what happens, it's actually probably a little easier to pull it straight from here. Okay, so once you've decided which way you're going to analyze, you can actually get my n values, my means, standard deviation, standard error here. Okay. Now, here's the tricky part about that. Okay, it matches because we didn't have any missing data. If you had some missing data that you decided not to fill in, and then you split the file and run the post-hocs, it might include some people that didn't get included in the overall ANOVA. So I included all the numbers from the ANOVA box because sometimes my t-test will lie to me about what these numbers actually should be. And this is a case for maybe you should delete people with missing data because otherwise they might get included in the post-hoc because it doesn't assume that you've run this ANOVA beforehand. Okay. But honestly, using it to calculate Cohen's d from this box would be a little easier. Okay. Now, I do have t numbers, so I'm actually going to expand, excuse me, expand this box here to be tp. Okay, so t and then degrees of freedom, because I have them. Okay? You don't get them when you run the Tukey stuff, but when you're actually doing a post-hoc, people kind of expect, when you're doing the post-hocs for interactions, people do expect you to have t values because they are there. So I'm going to include t, p, and then we'll calculate Cohen's d here in a second. Okay, so remember all the rhyming letters, t, p, and d. And so I'll get one for each one. So I got grocery, 07 versus 08, which is what I wanted to do. Now, remember, don't look at Levine's here. So this sig value, unfortunately, happens to match this one, but we're ignoring Levine's. So I've got my T, my D, and my P here. Okay. DF, sorry. So I got 35, 41. Let's see if I can stack these two where we can see both at the same time. So for grocery 07 versus 08, it would be T with, dear word, small lowercase t, 3541, okay, equals, and my T value here, 3.10. Okay, and my P value is 0.002. Alright, so what does that mean? Well, if I look at the means here, or in my box that I have up here in Word, I would say that means in 2007 I spent more money than 08 for grocery. We'll come back to D and do all of them at once. So for retail, I'm going to scroll down. So type of transactions says retail here. I got 07 versus 08, which is good. My T value would be 4.17 equals 5.01. P, is less than 001, because be sure you're looking at where it says SIG and not Levine's. And so what does that tell me? Looking up here at the means, I spent more money in 07 than 08. For entertainment here, I'm going to look at these numbers. So I got T is 3100, so 2.39. P less than P equals 0.02. So that actually would not, if I correct it, would not be significant, but I'm not. And so what does that tell me? Looking at the means, I just barely spent more money in 07 than 08. Okay. Down here under travel, we've got T is 3217. It's 3.12. My P value is 0.002 again. If I look up here at the means, again, 07 is greater than 0.08, sensing a theme here, but you've already seen the plot, so you knew this was going to happen. The last one, 3975 equals 2.41, and P equals 0.02 again, if I round up. And for my mean numbers, by just like $12, I spent more 07 than 08. Now, that's kind of boring, because look, the explanation is the same for all of them, which means that what is happening in my interaction? Like, what is actually going on? So interactions normally happen when the signs are reversed. Like, one is greater than 07, but this other one's greater than 08. So you kind of get this like flip-flop of your effect. But in this case, we don't. So this is another push for effect sizes, why you really need them, because that is going to tell me what my interaction actually is. So here I have that they're all 07 is bigger than all of them than 08, but for me, like, okay, great, fantastic, but why? What happened in my interaction? So I'm going to tell you which ones were larger than the others. So when the interaction's all in the same direction, what you really need to focus on is like which ones are bigger. So some of these effects are larger than others, and that's where D comes in. Okay, so I'm going to use this box. So in theory, you could combine my two little boxes here. I just think it's easier to talk about across or down in this type of box, and post-hocs in this one. Okay. What I'm going to do now is calculate Cohen's D for each one. All right, so I got 197.58 versus 185.33. I'll skip my two standard deviations because I have standard error. And then I definitely need N, so 1866 and 1677. Okay. So that first effect for Cohen's D, wow, it's really small, 0.07. Did I do that right? You know what? Looks like it. Okay, so it's really tiny. Oh, I can match my T values. Where's T? T, 1.97. I actually got a different T. What am I doing wrong? 1847, 1853, 4.27, 4.50, 1866. I don't know, maybe you guys will notice what's wrong. But my T values should line up. The degrees of freedom match, but T is a little different. Okay, I must have done something wrong somewhere. But we'll just keep trucking. 0.07. You get the idea. Unless I typed something wrong. 1957. Standard error. Okay, so I use standard errors. Here's another thing. So here's the standard error of these groups individually here, but I use the standard error from, sorry, I forgot about this, from my type of transaction box, and those are going to be slightly different because this standard error is controlling for the fact that they're all in one study, whereas when I run a t-test, this standard error is based on the fact that I'm only looking at these two individually, as opposed to it being one gigantic study. Okay. Both versions would be alright. I think what's going to happen if I use the ANOVA values is that my standard error is going to be, or my D's are going to be a little low. If I use the t-test values, the D's are going to be a little higher. And I don't know that there's any reason to pick one over the other, except maybe what I was saying a minute ago is this might be a little easier because it's all laid out right here for you within standard error, standard deviation. I think, like, theoretically, it might be better to do it from the ANOVA so you don't overestimate differences, but I don't know that I care if you do it as long as you are doing Cohen's D in some form. Okay. Alright, so I'm going to keep tracking with the numbers I have and realize that if you are doing it from your t-test, it will be a little different than these numbers. Alright, let's do retail. So 389.62. 52.5, 3.85, 4.0. Oop, not 40. No bad. Okay, got 2296 and 2123. So my Cohen's D is 0.20. Okay. And then let's do entertainment. So 253.63. 4.58, 4.79, 1619. Cohen's D is 0.07 again. So these are really small effects, which shouldn't be too surprising since eta squared was 0.001. Okay. So your D's will tend to match whatever your eta was. Okay. Like size-wise, not number-wise, because they're on different scales. Okay, 2090 and 1887. There we go. Okay, and 0.13. Oh, I skipped one. I think I just did other. Right? Okay, I skipped travel. Sorry about that. Okay. So 335, 0.45, 313.56. And 1504. And then Cohen's D 112. 12. There we go. So here's what the interaction is. So why did that interaction happen? Okay, you would see the same effect no matter if you use the numbers from the ANOVA, like I did, or the numbers from T. You would still get the same pattern. Your D values would be slightly different. And then just as a quick explanation, like why are they different? I know that probably is a little confusing. Essentially, this standard error is calculated from the ANOVA, is calculated based on the fact that like you're thinking about both variables at the same time. So it's not just thinking about this one cell, it's thinking about the fact that I have 10 of them. When I calculate it for D, for T values, the standard error is based on the fact that there's only 2. Okay? And so that's why these are slightly different. And I tend to do mine from the ANOVA because that's the way I was trained, but I don't know that it matters as long as you're consistent. Like, don't do half of them from the ANOVA and half of them from T. Okay. All right, so back to the question of, like, what is the interaction? Since I have them all in the same direction, like 07 is always larger than 08. Okay. And the reason we got this interaction is that these D values are not the same. Because some of these are larger than others, that's where there's this interaction. So there wouldn't be one if all of my differences were exactly the same. So this retail one is much larger than the rest of them, and then these travel and others are fairly similar, and then grocery and entertainment are the smallest pairs. And so we're getting the interaction because there are differences in the sizes of the effects. Okay, so this is one reason why I love effect size, because sometimes it helps explain things that maybe aren't totally obvious to people. Because if I were reading this and you said, 07's always larger than 08, and I'm like, okay, so why is there an interaction? You can then say, because retail has a larger effect for this than entertainment and grocery. I wouldn't want to say significantly larger effect because I didn't test that, but I can just say it's larger because I can look at Co and D. Alright, so all that being said, the very last thing to do is create a chart. Okay, you always end with charts. So I'm going to go back to SPSS. Alright, so let's go to Graphs and Chart Builder. So it's auto-selected bar, which is what we want, but this time we have two variables, so I'm going to use a clustered bar graph. So double-click on this clustered bar, or drag and drop. And then way I always think about this conceptually is that the one I sit here and cluster, this is essentially what is the legend, should be the one I am analyzing by. Because I want 07 and 08 next to each other in these little clumps, because that's how I analyze the t-test. So that makes it much easier for people to go, look, you did this t-test where grocery 07, 08 were compared to each other. So now in my figure, I want to see those bars right next to each other. The problem is that if I tried to dump year at the moment into cluster, it's going to tell me I can't, because your cluster variable here has to be nominal. So I'm going to right click on that bad boy and then change it to nominal. Because at the moment it's treated as a nominal variable. Okay, so I'm going to stick year into cluster, my other IV into X. I could switch those if I decide I don't like that version, and my DV into Y. Over here in the Properties window, display error bars. Make sure you hit Apply. I'm going to go ahead and see if I can change some of this stuff, so I'm going to make type of transaction more appropriate, so be sure you're capitalizing everything. Under Y, I'm going to do mean amount spent. I don't like that it says mean. I'm going to do average amount spent. Oops. Okay. I'm going to make the minimum 0 because I can't spend negative numbers. I'm going to let the maximum do its thing because there really isn't a top. Okay. And then I'm going to hit OK. Hopefully I hit Apply. Oh no, I did it again. I did this in class too. Okay, so we split file to be able to get these travel other separate files, and I forgot to turn it off. And so it's going to give me 4 or 5 separate boxes, but look how cute they are. So if you get this sort of thing and it happens, I did not do that on purpose. I did that because I'm forgetful. Go to Data and Split File and do Analyze All Cases. Do not create groups, and then hit OK. Okay. So I wish again I would say there's some sort of visual discrimination that split file was on, but there isn't. So now let's make that graph again. So Graphs, Chart Builder. I have it all still set up because I haven't closed anything. Hit OK. This time I should get the graph I was expecting. There we go. All right. So I like this graph because all the words are capitalized. Which is journal appropriate. I've got an appropriate y-axis, average amount spent, an appropriate x-axis, appropriate labels. So I have many times have I said appropriate. I've got my error bars. And this is what I was saying. I compared grocery 07 to 08. So these two little bars are what I compared to each other. And I could see that there's a bigger gap for retail than there is entertainment and grocery. So that really helps people see excuse me, what your posthocs were when you have them like clustered together. It's not wrong to do it the other way. It just, this matches what you were doing when you were running the test. Alright, so in the results section that I have on page 132, I don't have the whole thing written out, but I give you a basic idea of what's going on. You'll talk about your data screening, give a quick overview of the variables, because lots of times people will skip your methods section and just look at your results. Talk about the ANOVA, and there's two ways to do this. You can either talk about all three ANOVAs at once, like main effect, interaction, which is what I did in the write-up, and then have a paragraph for posthocs. So you could do like ANOVAs, t-tests, or you can do main effect, posthocs, interactions, posthocs. So you can cluster it by analysis. Both ways are okay. I tend to like to do here are all my ANOVAs, here are all my posthocs if I'm only going to analyze the interaction. And then if I'm analyzing like multiple different hypotheses, I might break it down by just like all of hypothesis 1, all of hypothesis 2. So it kind of depends on like what the goal of me trying to sell you the story is. But what you need to make sure you have in the write-up for that section is you always have to have the 3F tests, even if they aren't significant. So things that aren't significant aren't important. Like, don't just leave them out. So if they're not significant, it's still in there. So 3F tests. And then all of your post-hoc tests, again, even if they're not significant. A lot of our examples are because I make up this data, but that doesn't mean that you just leave it out when it's not. Okay, because people want to know about the ones that didn't work out, so they don't make that same mistake. So you have 3F tests and then all of the post-hocs that you ran. Okay? Which is sort of what I did in the write-up. And then you'll have a figure. So you'll notice that in my write-up I don't have any means, because basically it's C figure 1 for all the means. And then I have the figure on page 134, and people would be able to look at the numbers there. Okay? So if you have all of your averages in a figure, you don't necessarily need to type them all out in a figure or a table in the write-up. Okay? So make sure you have data screening, ANOVAs, and posthocs all in your write-ups.